Okay, so what we're going to do now is shut down the regular simple C that we're running just now, and we'll load up a more complex and realistic C state. Just tell the paddles to come down, and we've pre-compiled a C state that's the sort of C you would find on the west coast of the UK. We're now sending different signals to each paddle, and they'll all be making adjustments as they go to produce a much more complex and realistic C state.
We've been studying the reactions between moving machinery and water, which is something that has been understood for shipping purposes for not just decades but centuries. But understanding the physics of the interactions between moving water from both waves and tides and the machinery that is trying to extract the energy has sat at the core of the research conducted here at Edinburgh. I believe now that we have enhanced that understanding far beyond where it was even 5 years ago, and this has been very exciting to me, this relationship between engineering, the ocean and the environmental implications. There's no one way of harnessing the power of waves. Some devices respond by allowing air to be compressed within their structure and driving that air through turbines to generate power. The device that's currently being installed off Orkney, called Oyster, is effectively a flap which is attached to the seabed, and this simply moves back and forward and pumps seawater again through a turbine to generate electricity. One device looks a bit like a child's seesaw, and it swims back and forward a little bit like two linked fish's tails to generate power. The challenge for the engineer is to make these systems reliable and of course cheap, and most important of all, easy to install and easy to maintain.
This is a scaled down replica of a real three-dimensional sea state. It looks quite small, but if you imagine that we're normally working at a scale maybe of 1/100th, then we would be about that size. And we can take a device, a model that we might be testing, and we can test it, then we can make a very small change to it. One change, put it back, repeat the test. Is it better or is it worse? Now in real life, the weather would have changed. Everything would have changed, but in the tank, only one thing changes.
It is possible to make estimates of the ultimate energy capability within a particular tidal area or a particular wave area. But what we've been looking at as part of our research is just how much of that energy can we realistically extract without seriously compromising the resource itself and of course the environment.
What you're looking at here is a model of a tidal channel. At the far end from where I'm standing, you could imagine that that's the Atlantic Ocean, and at this end where I am, this could be the North Sea, and the flow's then flowing between the two oceans a bit like it does in the Pentland Firth, with the land, the islands on one side and the Scottish mainland on the other, concentrating the flow and accelerating it. We can use this to look at what the effects of extracting energy from this channel would be on the overall flow, and we can use it to understand what the turbulent structures look like as the flow comes through the channel.
At present, marine energy is making a very, very small contribution to our energy supply. We're really only talking about demonstration devices. If we're thinking about making measurable proportions of the country's electricity need, we really need to be looking 10, 15 years into the future, towards 2020, when we hope and anticipate that we'll be seeing something of the order of 2 gigawatts installed capacity of marine renewable energy. 2 gigawatts would be roughly equivalent in terms of capability to a large nuclear power station, which is a sizable contribution. At the moment, the devices are installed individually. It's a difficult, expensive process, and we cannot pack them closely together. That's a challenge that we believe we can overcome. In addition, the present generation of tidal current systems really do not like highly energetic wave environments. We need a new generation which can extract power from the tidal currents whilst being exposed to significant wave forces. Again, to achieve that, we need to draw upon present and future research.
Many countries around the world look at the research and development programme in marine energy in the United Kingdom and are desperately trying to emulate the initiatives and to follow the lead that the UK has been demonstrating in research and development. We have to maintain that position. There is an opportunity to create wealth and to create employment that will be able to develop a clean, lower carbon energy source from the sea for the future.